Hello students, welcome to this presentation on design of the bevel gears, and in this presentation we are going to look at the procedure of designing the bevel gears. And see, this is the way the bevel gears look like. So this is the gear and this is the pinion, and this is the axis of the pinion, axis of the gear, and somewhere they intersect here. Now see, actually it is nothing but a cone. If you extend this, it will look like a cone. Similarly, if you extend this, it looks like a cone, but that material is removed. So these are means the teeth are cut on the frustum of the cone, and the power can be transmitted between the shaft of this and this, which is maybe around 90 degree or less than 90 degree or more than 90 degree. Now let us look at some of the terminologies that come in bevel gear. So this is the shaft angle. Shaft angle means the axis of the pinion shaft and the axis of the gear shaft intersect here. This can be 90 degrees or less than 90 degrees or more than 90 degrees. And wherever these two intersect is the pitch apex. And this is the outer cone distance, this is the back cone angle, pitch diameter, outside diameter, and this is the back cone distance, and this is the back angle. And in this figure you will see this is the pinion and this is the gear, and this angle is called as shaft angle, denoted by angle theta. So theta may be 90 degree, less than 90 degree or more than 90 degree. And this is the pitch angle or semicone angle for the pinion, denoted by delta 1. And similarly, this is the pitch angle or semicone angle of the gear, denoted by delta 2. Now with this basic information, we will move on to the design procedure of the bevel gear. And here this slide shows various forces coming on the bevel gear tooth. So this is the load coming on the gear tooth F, and if it is resolved, we will get the tangential load Ft, the axial load parallel to the axis Fa, and radial load perpendicular to the axis. And we are interested in this component of the load, that is Ft. Now, as a first step, we have to determine the velocity ratio if not given. Then find the semicone angles delta 1 and delta 2 of pinion and gears depending upon the case. First case is if it is an acute angle gear, means when the shaft angle is less than 90 degree. In that case, this is the equation for semicone angle of the pinion, and this is the equation for semicone angle of the gear. And these equations are available as 12.29a and 12.29b on page 215 of Design Data Handbook by Mahadevan and Bevel Reddy. Then second case, when theta equal to 90 degree, these are the equations for determining the semicone angle of pinion and gear. And third case, when theta is greater than 90 degree, these are the set of equations which are used to calculate the semicone angle for pinion and the gear. The next important step in this procedure is to determine the virtual number of teeth on the bevel pinion and bevel gear. This equation is simple, ZE equal to Z divided by cos delta, and is available in the data book as equation 12.35d on page 218. The next important step is to identify the weaker member among the pinion and gear. Now as usual, you have to determine the product delta D1 and Y1 for pinion, delta D2, Y2 for the gear, and whose member's value comes less is the weaker member. Now after comparing the values of these two, the member with smaller value of sigma d into y will be the weaker member, and that member will be designed. Once that is decided, which is weaker member, then we go on finding the tangential tooth load based on the power transmitted. Again, standard equation is there: 1000 into P into CS by V. CS is the service factor available in this table on page 235, and V is pitch line velocity, pi dl by 16 into 1000. Then again, by using the Lewis equation, we need to find out the tangential load Ft, and in this case these are all common when compared to the spur or helical gear. This is the extra term coming in the design of the Bevel gear, L minus B by L. Okay, so already we have seen L as the cone distance, B is taken by L by 3, capital Y equal to pi into small y. This is Lewis form factor, and L is calculated by using this relation, which is dependent on the pitch circle diameter of the pinion and the gear, or number of teeth on the pinion and gear, and of course module term will be there. Then comparing the tangential tooth load equations, that means calculated from the power transmitted and calculated from Lewis equation. After comparing, put that in the form MQ into CV, so something value you will get here, and by assuming CV equal to 0.5, M can be calculated, and see that this side is greater than this side for chosen value of CV as well as module. Then once the module is fixed, find out the dimensions or parameters of the pinion and the gear. So these are the set of equations available in the data book. Then important step is to find out the dynamic tooth load by using this equation, and wear load by using this equation, and the condition to be satisfied is wear load must be greater than the dynamic load. When these two are compared, by comparison we get the value of K. Choose the value of K from the data book, standard value of K, and then based on this find out the relent harness number of pinion and the gear, which are available on page 239 table, and that completes the design procedure of the Bevel gear. Thank you, students.